There are over 700 programming languages in the world. 700. And somehow, every internet argument boils down to about 5 of them. But here's what most people miss. Languages aren't random names on a list. They fall into real types. Categories that explain why Python feels nothing like C. And why some languages scream at you before your code ever runs. This is every programming language type, explained. Machine code. Every fancy language you've ever heard of eventually becomes this. Machine code is pure binary, ones and zeros that your CPU reads directly. It's the native tongue of your processor. No interpretation layer, no middleman, just raw instructions hitting silicon. Think of it like giving someone directions in their home language versus going through 3 translators. Machine code skips the translators entirely. The critical thing to understand is that it's architecture-specific. Code for an Intel x86 chip won't work on ARM. They speak completely different dialects. So why don't we all just write machine code directly? Because it looks like an endless wall of ones and zeros. Nobody has time for that. It's not a skill flex, it's a sanity risk. You'd never choose to write in it today. But understanding it matters if you want to know what your computer is actually doing underneath everything else. The myth that it's irrelevant couldn't be more wrong. It's the foundation everything else stands on. Assembly language. If machine code is the CPU's native language, assembly is the phrasebook. It replaces binary strings with short readable commands like MOV, add and JMP. You're still talking directly to the hardware. You're just using words instead of squinting at binary soup. Assembly sits one tiny step above machine code. It gives you total control over the processor. It's like driving stick with no power steering. You feel everything. That's both the thrill and the terror. The key spec is simple. One assembly instruction maps to one machine instruction. Zero overhead, maximum responsibility. You'd reach for assembly in embedded systems, OS kernels, or security research. Anywhere microseconds actually matter. For everyday app development, it's massive overkill. The common mistake is thinking assembly is dead. It's not. Every major operating system has assembly buried in its guts. Game console developers still use it for critical performance loops. It's niche, sure, but it's breathing just fine. Compiled languages. These are languages where your entire source code gets translated into machine code before anything runs. You write it, a compiler chews through it. Out the other side comes a standalone program your OS runs directly. C, C++, Rust, and Go all live here. Think of it like baking a cake from scratch. There's prep time up front, but once it's done, it's done. The defining trait is speed. Compiled programs run fast because the heavy translation already happened. The specs that matter are compile time, runtime performance, and binary size. Rust compiles slower but produces incredibly safe code. C compiles fast and runs fast but trusts you completely. That trust is dangerous. Choose compiled languages for game engines, operating systems, or anything performance critical. If raw speed is the priority, this is your lane. The biggest myth? That compiled always means fastest. A sloppy C program will lose to well-optimized Python with the right libraries. How you write the code matters more than what translates it. Interpreted languages. The opposite philosophy. Instead of translating everything up front, an interpreter reads your code line by line and executes it live. Python, Ruby, and early JavaScript all work this way. It's like reading a recipe out loud and cooking each step as you go, no memorizing the whole thing first. The defining trait is immediacy. You write code. You run code. No waiting for compilation. That feedback loop is fast and honestly kind of addictive. The key spec to understand is overhead. The interpreter translates every line every time it runs. That adds a performance cost. Pure Python is slower than C for raw number crunching. But here's the thing, if you're building a web app, prototyping a tool, or learning to code, speed of development crushes speed of execution. Interpreted languages let you move fast. Most modern interpreters also use tricks like just-in-time compilation to close the performance gap. The myth that interpreted automatically means slow is years out of date. The line between compiled and interpreted is blurrier now than it's ever been. Statically typed languages. This is where things get spicy. In a statically typed language, every variable gets a fixed type before the program runs. You say this is an integer, it stays an integer. Java, C#, TypeScript, and Rust all enforce this. Think of it like labeling every container in your kitchen. You always know what's inside. You can't accidentally pour milk into the sugar jar. The defining trait is safety. The compiler catches type errors before your code ever executes. The spec that matters most is type inference. Modern languages like Kotlin and TypeScript can figure out the type without you writing it explicitly. You don't always need to spell everything out. Choose static typing for large codebases and team projects. Catching bugs at compile time saves serious hours later. The common mistake is thinking static typing means writing way more code. With modern type inference, the difference is barely noticeable. If you've ever had a bug in production because a string snuck in where a number belonged, static typing is exactly the fix you wanted. Dynamically typed languages. The free spirits of programming. In these languages, types get figured out at runtime. You don't declare them up front. Python, JavaScript, and Ruby all work this way. A variable can hold a number right now and a string 2 lines later. It's like a shelf where you toss whatever fits. Convenient, flexible, and occasionally chaotic. The defining trait is development speed. Less boilerplate, fewer declarations. You just move. But types still exist here. They're checked while the code is running, not before. Duck typing takes it further. If it walks like a duck and quacks like a duck, the language treats it like a duck. Choose dynamic typing for prototyping, scripts, and smaller projects where flexibility beats rigidity. The biggest myth is that dynamically typed means no types at all. That's wrong. It means type errors show up later, at runtime, sometimes at 3 in the morning while you're debugging something that worked yesterday. That's the trade-off. Freedom up front, surprises down the road. Procedural languages, the original way humans organized code. Procedural languages break programs into procedures, step-by-step functions that run in order. C, Pascal, and Fortran are the textbook examples. Think of it like following a recipe top to bottom. Step 1, then step 2, then step 3. No detours, no surprises. The defining trait is straightforward control flow. You know exactly what happens and when it happens. Predictable, readable, and for a lot of problems, genuinely all you need. The specs that matter are function libraries and sequential execution. A clean procedural program has reusable functions that each do one job well. Choose procedural for learning to code, scientific computing, or simple automation. You don't need objects, you don't need monads, you don't need anyone on Twitter telling you your paradigm is wrong. The common mistake is calling procedural programming outdated. The Linux kernel is procedural. Massive physics simulations run procedurally. It's not trendy. But trendy and effective are two very different things. Object-oriented languages. This is the paradigm you've probably heard the most about. Object-oriented programming organizes code around objects, bundles of data, and the functions that act on that data. Java, C++, C#, and Python all support it. Imagine your code as a bunch of Lego kits. Each kit is self-contained with its own pieces and instructions. You snap them together to build something bigger. The defining trait is encapsulation. Objects hide their messy internals and show only what's needed. The specs that matter are classes, inheritance, and polymorphism. Classes are blueprints. Inheritance lets one class borrow from another. Polymorphism lets different objects respond to the same command differently. Choose OOP for large applications, game dev, and enterprise software. It scales well for teams because objects create natural boundaries. The biggest myth is that everything should be an object. Overusing inheritance creates tangled webs worse than the spaghetti code OOP was supposed to fix. If you've ever seen a class called Abstract Singleton Proxy Factory Bean, you've witnessed this problem firsthand. Functional languages. Here's where some people's brains start to melt a little. Functional programming builds everything around pure functions and immutable data. You create a value. It never changes. Haskell, Erlang, Clojure, and Elixir live in this world. Think of it like a math equation. Same input always gives you the same output. No surprises, no hidden side effects. The defining trait is predictability. Pure functions make code easier to test, debug, and run across multiple processors. The key specs are immutability, first-class functions, and recursion. Functions get treated like any other value. You pass them around. You return them. You compose them together like building blocks. Choose functional programming for data pipelines, concurrent systems, or financial software. Erlang literally runs most of the world's telecom systems. The biggest myth is that this is only for academics. If you've used map, filter, or reduce in JavaScript, you've already done functional programming. You just didn't know it had a formal name. Scripting languages. If you've ever written a quick file to automate something tedious, you've used one. Bash, PowerShell, Lua, and Perl are the classics. These languages glue systems together and handle repetitive grunt work. They're the duct tape of programming. Not elegant, but incredibly effective at holding things together. The defining trait is convenience. Quick to write, quick to run, minimal ceremony. The key specs are ease of use, built-in system access, and library ecosystems. Bash gives you direct access to your operating system. PowerShell does the same on Windows. Lua is tiny enough to embed inside game engines, like a quiet roommate who always pays rent on time. Choose scripting for DevOps, automation, and configuration tasks. If you're renaming 1,000 files, scripting handles it in minutes. The myth that scripting languages aren't real programming is hilarious. Tell that to the DevOps engineer whose bash scripts keep your favorite website running at 2 in the morning. Markup languages. This one starts fights. Markup languages structure and format content. They don't execute logic. HTML, XML, and Markdown are the big names here. HTML tells your browser where headings, paragraphs, and images go. XML structures data for machines to read. Markdown lets you write documentation without a degree in formatting. Think of markup as the blueprint for a house. It shows where everything goes, but it doesn't pour concrete or wire electricity. The defining trait is structure over logic. No loops, no variables, no conditionals. The specs that matter are tag syntax, nesting rules, and rendering support. HTML5 is the skeleton of every website you've ever visited. Choose HTML for anything on the web. Choose Markdown if you value your sanity while writing docs. Now the myth everyone loves to argue about. Is HTML a programming language? It's not. The name literally says markup language. But it's essential, and knowing it well is a genuine skill. Drop your hot take on this one in the comments. Query languages. Last stop. Query languages exist for one specific job. Talking to data. SQL is the undisputed king. But GraphQL and Cypher have carved out solid niches. When your app needs to pull a user's order history or find every product under $20, a query language handles it. Think of SQL like asking a librarian a very specific question. You describe what you want. The database figures out how to find it. The defining trait is declarative syntax. You state what you need, not how to get it. The key specs are database compatibility, join performance, and indexing. A well-written query finishes in milliseconds. A bad one brings a server to its knees during lunch traffic. Choose SQL if your app touches a database. That's basically every app ever built. Learn joins, learn indexing. Seriously, the myth that SQL is outdated gets repeated every few years. Some new NoSQL trend gets hyped. Everyone migrates. Then everyone quietly migrates back. SQL has been around since the 1970s. It's not going anywhere. So there it is. From raw binary that only your CPU can stomach, through assembly's zero hand-holding approach, past the compiled versus interpreted divide, into the typing wars and paradigm battles, and all the way down to politely asking a database for your data. Every one of these types exists because someone had a problem and said, there has to be a better way, and honestly, they were usually right. If you made it this far, you already understand more than most people who just picked a language because Reddit told them to. What was the first programming language type you used without knowing what it was called? Drop it in the comments. Hit the like button. It genuinely helps the channel more than you'd think. And if you want to know which actual languages are worth learning right now, that's exactly what the next video covers. Click the video on screen right now.